I've been doing for 40 years, I've been doing this relativity stuff, trying to figure out what's going on. And have you seen any talks on anybody who was opposed to Einstein, you know? Yeah, so that's kind of, definitely a censorship, and we do that. I've been an editor too, and I would reject papers that were nonsense. Now you have to know what's nonsense and what's sense, so that's the problem. That's what Einstein was using. That's why he objected to quantum mechanics, because they didn't have any real good proof. It was more bullshit than he had even. Time can dilate. Time doesn't dilate. Time is motion. Remember, all the experiments have to prove Einstein's right. Like you were mentioned, I think, isn't there a cult here? Yes, that's indeed the case. Somebody says time is an object like Einstein did, or a dimension. I always ask them, give me some time, and I'll put it in my back pocket. I'll keep it around to write my next book. Einstein then, I say, and I think this is true, he didn't know what time was, because he would have never used time as a dimension. It's not a dimension.
Did Einstein mean it that is like literally a dimension of space, or is it, and the physicists are just trying to split it?
He was literal, and that the guys you're talking about are wrong. We have about 10,000 dissidents who all have objections to this kind of stuff. They don't say, oh, Darwin is right again, because that's not news. But every time Einstein is right, that's news, and so on.
So I said, like, so what's going on? And it said that it's programmed to fabricate and make up information in order to defend relativity.
Is that right?
Yeah, I can show you. I have it on. I have like a screenshot of it. I can even send it. Yeah.
I'd love to have the copy of that. A lot of people think time is a measurement. You know, like they mistake the clock for the motion. This commonly happens.
Ah, yeah, that's a really good way to put it. I think that's where people get confused.
In relativity, one of the silliest things is that mass is converted to energy. And energy is matterless motion.
Not only children need a bit of thrashing, but also grown-ups, and especially women.
Another Einsteinism is to glorify Einstein on every possible occasion. And this would be an example of how you would do that by not mentioning any of the scandals involving his personal life. Well, remember Einstein said, imagination is wonderful because it goes around the earth, religion is based on dreams and imaginings, right? And a lot of our math is based on dreams and imaginings.
First thing I guess I should ask is, what is your physics background? A lot of the viewers will probably be wondering.
I did my PhD in nuclear physics. Actually, I was using a TRIGA reactor. That's a common reactor on campuses. And we were doing volcanic ash correlation. And so what we wanted to do is make these little 1-gram samples radioactive. And we would get about 25 elements as a result. And then we would detect those and measure the peaks from each of them, so we could measure how much was in each sample and compare one volcano with another. So we were looking at soil, so we wanted to say, well, is this soil from Mount Mazama, which was from Crater Lake, or is it from, well, Glacier Peak, which is closer to where you are, towards the border, or from Mount St. Helens, which erupted after our work. We predicted that sort of, and it erupted in 1980. So anyway, that's what I did my thesis on, and at one time I was offered a position as a visiting prof in Brazil to teach nuclear physics, in Portuguese, no less.
Ah.
And they had a fascist government at the time, and I thought, they're probably looking to get a nuke or something, and I would be the guy to start that up, and I kind of passed on that one. So I ended up then actually working for the state of California as a geophysicist, geochemist, and in working on earthquakes and landslides and all kinds of really interesting stuff for 30 years. So, and now I'm still doing a little bit of consulting work on earthquakes where I use soils to get the ages of the faults and so on. So,
Okay. Well,
and so I've been doing for 40 years, I've been doing this relativity stuff, trying to figure out what's going on. And
holy
I'm a
moly.
farm kid from Wisconsin, and grew up on a dairy farm, and we are very practical. I'm very simple-minded, and all the complicated stuff that Einstein came up with is doesn't turn me on at all. And as I once mentioned, one of the C's I got, only a couple C's in college, was on Physics 1A, and they taught this cartoon type book on relativity, and I couldn't do four dimensions and all that stuff. And so consequently, I took Physics 1B during the summer. I said, I'm going to get this right. So I did Sears and Szymanski, taught by this 83-year-old fella, and it was mostly Newtonian, and I did every one of the problems and everything, and got an A plus in that one. So uh, that shows you the difference between
Right.
provability and not.
Okay, well, I'll try to keep this interview moving. I have a lot of questions for you. So let's go right into this. You have definitely quite a background here.
Sure.
Okay, so my first question is, let's say you only had a couple minutes to live, and you have to convince somebody that relativity theory and Einstein is nonsense. What's going to be the strongest, most convincing argument you can give?
Well, it was already done back in 1908 by Sagnac, and I don't know if you can see this. I've got a figure. If you have a source that's rotating and a detector that uh, I think it was rotating. No, I'm not sure it was rotating, but anyway, the light arrived and produced a fringe as a result of that experiment, which showed that it was a wave and not a particle. That's essentially what it was. And then the other one that I like is the little figure we have here on figure 3 in Religious Roots, I think it is. Let me see.
I'll
take a
write all
look at
these.
it.
I'll write all
Yeah,
these down,
it's
and
on
you can send them
page
after.
38 if you got a copy, and it's figure 3. And notice the different values for that measurement of what Michelson-Morley were trying to do. And what they were doing is trying to measure, obviously, you might have explained this before, but essentially, headwind that the Earth would have if the ether was fixed.
Right.
And so I use the spelling with an E for fixed ether, which doesn't exist, by the way. Actual ether is, like Descartes said, it was spelled with an A instead of an E.
Right.
And that is the correct. Now, the reason he couldn't get any result was that the ether is really attached to the Earth. So you can't measure any difference like you would if you actually had the Earth moving through the ether that was fixed. So that was what they did, and what this figure 3 shows in religious, and it was essentially they called it a null result. So no result. So as Galeev, this fellow in Ukraine, measured it in various ways. He used light and he used, I believe, sound as well. And anyway, and actually, Michelson did an experiment in 1926. Remember the first experiment, 1887. That's the one that Einstein used. He didn't refer to it, but that's where they said there was no ether. So anyway, that's essentially what he was working on, and then declared there was no ether. Obviously, if there's no ether, then you have perfectly empty space, which has all kinds of philosophical ramifications, which is really explained in Religious Roots, because that was kind of the theme I did in that book, essentially to emphasize that what he said was you had perfectly empty space, inside photons, which were massless, therefore, and these photons were traveling over long distances through perfectly empty space, nothing happening to them. And of course, there's nothing in the universe that doesn't lose energy over distance. So that was the problem. So he invented these 8 ad hocs, which I had pointed out.
Yes.
And that was the main one right there.
No, so sorry.
How can you have a massless particle?
In the interest of time here, I'm just going to try to kind of cut some time off. So you're saying in this Sonyak test, they proved that light is a wave, right? So how do you go from light is a wave to relativity is incorrect?
To a particle? Well, yeah. See, one of the reasons that, remember, Einstein got only one Nobel Prize. It wasn't in relativity. It was on kinetic energy. Essentially, had to do with the electronic effect that you get when light hits I guess an anode or whatever. It shows that light has a particle characteristic. Okay?
Right.
And that's because it's in a medium, just like your sound travels through a medium that's filled mostly with nitrogen in the atmosphere, right?
Right.
So that's essentially what he was going on, and so this impact that he was measuring that got him the Nobel Prize was what impressed him probably most. And it's like for a hammer, everything's a nail, and so that's what he essentially ended up doing, not double checking his work after he came up with absurdities and all the silly stuff that is currently being pushed.
Right. This is your 5-minute disproof by evidence. You're kind of giving evidence Einstein is wrong. If you had to give a proof by logic, like let's say you're just looking for an error in the reasoning, like the logical reasoning of Einstein, what would be the most compelling argument you could give or a disproof of relativity through logic?
His idea that time can dilate. Time doesn't dilate. Time is motion. Motion can't dilate. Only things can dilate. That's one of the silliest things that come out of his work. And he totally missed up on that. Even Wikipedia shows that if you've got two things that are moving apart, the distance between them increases, right? And I think I saw your thing on Doppler effect, and that's essentially what's happening in the twin paradox, especially. All you got is, in one case, when something's going away, the wavelengths are longer because there's a gap process right between the two parts of the wave. So anyway, you have that, and then when something comes towards you, the wavelengths get shorter. And instead of doing that, what they've done, one of the experiments on that is Pound and Rebka in 1960, where that's a famous experiment that proves Einstein's right. Remember, all the experiments have to prove Einstein's right.
Right.
Because that's how this works. It's like your religion is always right, and almost 4,000 religions are wrong. That's how that works. And so, like you were mentioned, I think, isn't there a cult here? Yes, that's indeed the case. And so you have to believe that. And so dilation is used by Pound and Rebka in 1960. They had this tower where they actually evacuated it. They just put helium in, which wouldn't have an influence. And they found out that there was a redshift for electromagnetic radiation going away from Earth, and a blue shift for that radiation going towards Earth. And they did that only over a short 22-meter tower distance. So it was perpendicular, of course, to the Earth. And so they did that, and then they said, well, this difference is due to time dilation.
Right.
But what it was really due to was the fact that ether density, like we've shown in these higher altitude things, ether density increases with distance from the Earth. And that's because the ether particles there have not yet collided with ordinary matter. And so when it does, like when it hits the Earth, these ether particles produce gravitation, and so they end up slowing down as a result. and they're decelerated, and that's why my theory of gravity is called ether deceleration theory, because that's what happens. And so it's sort of the result is sort of the reverse of the atmosphere. Remember, the atmosphere gets thinner and lower pressure distally, and that's further away, whereas ether is just the opposite, because it's what's out there before that ether has collided with anything. And ether will have different pressures all over the place. It depends on, of course, the mass that it's colliding with. So bigger mass, like the Earth, will have more deceleration than, say, the Moon, which has lower deceleration. But it also has the same thing, that the speed away from the Moon actually increases. And so when the speed of a electromagnetic radiation increases, the wavelengths get longer.
Right.
And one good example of this is if you consider water. The speed of light in air is 300 million meters per second, and in water it's 225. So it's slower. Well, what happens to the wavelengths? Well, that changes too. They get smaller in water than they are and the frequency, however, is the same in both, which is kind of interesting, because normally physicists think frequency is related one-to-one with wavelength, but in that case it isn't. And in case of this whole idea of changing from close to far away from the Earth would do the same thing. So yeah. So anyway, there are all kinds of things. One of the things, I don't know if there's what's called the Shapiro slowdown or whatever, that occurs when light passes a planet with an atmosphere. Remember, water is 225, air is 300. So if there's a little water in the atmosphere, what's going to happen to light? It's going to slow down.
Right.
And of course, that's what happens. That's what the index of refraction tells us. When you look at jewelry like diamonds, you have an index of refraction,
right.
which means that's the equation for slowdown of light. And because the ether particles that are part of the wave motion, they're interfering with the actual matter that's involved.
So to go back to the point you were saying, you're saying time cannot dilate.
Right.
So maybe can you elaborate a little bit more on why can time not dilate? So, and what do you mean by
Because it's
dilate?
not a thing.
What does dilate mean?
Remember, this is how we do in PSI and progressive physics. What we do is we talk about time as motion, and matter is an XYZ portion of the universe.
Right.
So anything that has XYZ dimensions is matter, and if you examine it, there'll be matter inside and be matter outside. And so that's what that is. And so here, you're talking about the matter versus motion. Motion doesn't exist, it occurs. That's why time isn't, like if somebody says time is an object like Einstein did, or a dimension, I always ask them, give me some time and I'll put it in my back pocket. I'll keep it around to write my next book. That's not going to happen. That's just not going to. So that's what. So anyway, so it's silly. And Einstein then, I say, and I think this is true, he didn't know what time was, because he would have never used time as a dimension. It's not a dimension. And people have talked now about string theory with its umpteen dimensions, I don't know, they're probably at 26 by now. And all that is silly stuff. And it's a takeoff from Einstein. Once you use Riemann's stuff and all the stuff about other dimensions you can do in math. In math, you can use time as I use it all the time. One of the dimensions in some of my graphs show time. I'm looking at soils that are young, soils that are old. So on one side they're young, on the other side they're old, and that's my time scale.
Right.
But that doesn't make time a dimension.
Okay, I want to make an interjection here, because you said that time is not a dimension of space, and I think pretty much everyone would realize, if you're going to say this is the length, width, height, where's the time dimension, right? It's very
Yeah,
absurd.
yeah.
But when you challenge, let's say, a physicist on this, they're going to say, "Oh, we don't mean time is a literal dimension of space. It's not a spatial dimension. It's like this, just this fourth coordinate. So you have an x coordinate, a y coordinate, a z coordinate, and then you'd say it like this. This is like the time coordinate, and then at this time it's here. Like they use it kind of like that. You know what I mean? Is that just them trying to like kind of save what Einstein said? Did Einstein mean it that it's like literally a dimension of space, or is it? And the physicists are
No,
just
no,
trying to save it? Or?
he was literal, and that the guys you're talking about are wrong because the cosmogonists, and I use the word
Oh,
cosmogonist,
huh.
remember, as someone who assumes the universe had a beginning. So cosmogonists talk about not a beginning, but a finite universe that's expanding, and the only way that can happen without it coming from a point, nobody ever has said, well, the point is the Earth. That's where it's expanding from. The probabilities are with 20 trillion, 20 trillion galaxies. It's not possible. So that's what they were doing with that. And so you need that. You need Einstein's uh, uh, general relativity theory in order to have the Big Bang. You
Hmm.
can't. It doesn't work any other way. Because
So,
then you would not have an expanding universe. Is what? See, they're misinterpreting the Hubble effect. You remember that light just simply loses energy over distance. That's all it does. And the complications they have with it speeding up and all that kind of stuff, that's all just BS.
right. So, in the interest of time here, we're only on the second question, but we're
Yeah,
almost
okay.
halfway through our time.
Yeah.
Well, time's just a dimension of space, so we don't need to worry about that, right? Um, so, my third question I'll throw at you here is relativity designed in a way to be unfalsifiable? What would be the easiest, most practical way to falsify it, if it is falsifiable, in your view?
Well, it's been done many times. We have about 10,000 dissidents who all have objections to this kind of stuff. A lot of them have done experiments and so on. And like I said, with Galeev in Ukraine, who did this measurement at different altitudes, he's one. And Michelson is one. A fellow named Miller at Case Western, where this famous experiment was done by uh, Michelson, Morley. So all that disproves it right there. See, that's not the problem. The problem is the cult-like belief. Remember that Sonia came out uh, in 1913. It's only 8 years after Einstein's thing, and it definitely proved that light was not a particle. And yet these guys accepted the idea it was a particle, and there were all kinds of reasons for that, as I explain in Religious Roots of Relativity, which,
Hmm.
by the way, I should hold up so people can see what that looks like. I don't know if
This is
that.
an excellent book. I recommend buying it. I bought it, and yeah, if you're a skeptic of relativity, this dives a lot deeper into it here, and we'll get into this book a bit in this interview if we
Yeah,
have
I
the
can
time.
show you that one, this thing here. Okay, here, I don't know if you're going to be able to see that. You see that?
It's a
That's
little
the curve.
blurry.
Yeah, those
Oh, there.
those are
No, now
high.
we can see it. Yeah.
Those are the altitude is the left side, the y, and then the x is the uh, velocity that's calculated as a result. And so that is an example of all these data points disprove Einstein. So how many more do you need? And there have been thousands of experiments have been done, and these are only a couple that I showed. And that's where we're at. So that is not the problem. The problem is basically that he used religious assumptions like perfectly empty space. There's no such thing. What that would mean is that uh, non-existence is possible. Now that's not possible. Non-existence is not possible. That's why we have pushed the infinite universe theory. Because some matter exists everywhere. Remember, the first falsification on all this stuff, cosmogony in particular, is the first law of thermodynamics. You know
Right.
what that says? Says that energy can neither be created nor destroyed, which I call matter and the motion matter can neither be created nor destroyed. That's it. You're done. There's been no disproof of that ever. And every time it's proven, not proven, but supported, is a proof against Einstein. And people don't realize that. They've got all kinds of, so that's why I did the 10 assumptions of science, and that's called what I call conservation, as opposed to creation. Creation is the opposite, because it says you can create something out of nothing. And remember, that's very important for religion, because religion wants to have a creation, and almost all religions do. They're wondering, well, where did it all come from? That's the question they ask. And the Templeton Foundation will give you millions of dollars just to do experiments that prove that, though they've never actually proven anything like that. But that's what that's all about. And so that, and now 80% of the people in the world are religious. So how are they going to give up the idea that there could be nothing? And remember, there's a continuum. Empty space is an idealization. On one side, you have empty space. The other side, you have solid matter. That's what we call a continuum in science. Those are idealizations. They're imaginings. Right. They don't exist. No empty space exists, and no solid matter exists. And of course, that was the surprise that the Greeks had, because they talked about little tiny objects, atoms, they thought that were solid matter, and then they were surrounded with space, empty space, and so on. So that's was thrown out, because look at hydrogen has so-called empty space, 99%, but the rest of it is matter. And so, and that's true of all atoms. They all have what you would call empty space. Usually it's filled with ether, of course, but nevertheless, we could call it empty space. But it's not really empty space, you see. It's right. It's space, I suppose you can say, because there's difference from one place to another.
Okay, so I'll put you up to question 4 here. What are some of the most absurd and ridiculous arguments you've heard on relativity coming from physicists?
Well, I have this website on medium.com. It's called Infinite Universe Theory. So if anybody's interested, they can do that. I should point out some other books too here before we go on. A lot of silly stuff I mentioned here. This is Infinite Universe Theory, and then this book was the first one I wrote in '04, and this is the 10 Assumptions of Science. Oh. And of course, Religious Roots of Relativity, which is this one, actually is has the religious assumptions in opposition, and then of course my magnum is this one, Scientific Worldview. By the way, this is coming out with a 2nd edition now, so if you like to read a lot, this is the one right here.
Well, for a future interview, we might go into Big Bang and some more of the more cosmology.
Yeah, right. So let's see. Your question: what's the silliest?
What's the silliest things you've heard? Yeah.
The latest one was this guy Krauss from Arizona State.
I follow Krauss. He
says that the universe was a quantum fluctuation. Okay, and that's universe popped out of that. And now the latest has been that they talk about the possibility of the end of the universe being a quantum fluctuation, and that it could happen anytime. Everything would all of a sudden fluctuate and then we're gone. So those are one of the silly. The other one is the heat death of the universe, where they use the second law of thermodynamics, which says everything that's isolated comes apart, which it does. The only thing is, in an infinite universe, the parts go somewhere else. They don't just disappear. Nothing disappears, according to conservation, right? So that's one of the examples of how silly things can get. And of course, you got all this dilation stuff and so on. And remember the twin paradox, which is easily explained by a Doppler effect, coming and going. So I've got, I think, almost 90 on medium.com, about 90 posts. And if you have a question, you just can do that. You can also go to my PSI website, Progressive Science Institute, and it's scientificphilosophy.com, and you go there and you can see where the blog is. There's a blog on it where I've been doing, oh man, this for like more than 10 years. I've gotten a whole bunch of posts there, and if you have a question, you can just put it in. And also, on Medium, you can put in a response and put in a question. You got a problem, just send it to me, and I'll think about doing it. If it's got to be in the form of a question. I will get some of the regressive physicists complaining about, how I posed their view and so on, and but they never ask the question. They're also reformists who are probably mostly religious, and they are trying to. A reformist tries to use Einstein's relativity to get published or whatever, because the remnants of that are still around, of course, and they would use that to try form their own theory, and which is always a failure because, like for example, a lot of them probably think that light's a photon, a particle,
Right.
and that blows you out right away. Or they deny there's ether, that blows you out too. So there's all kinds of things like that the reformists are trying to do, and a lot of that's pretty silly too. And so it's just what's happening.
Okay. Next, I was going to ask you. So I give these Princeton and Caltech physicists the same basic questions on relativity, and they gave me totally contradicting answers. So, for example, like I'll ask them a question like, you have two rockets that are identical flying by each other in outer space. They should both see each other's clocks as like slower, the same time, or running faster, right? And one physicist will say like they'll both view each other's clocks as slower, and the other will say they both view them as running at the same time as they pass each other. So like my question is, how can they possibly be getting the calculations correct if they're applying different calculations to the same scenario? And would you like to see a wide-scale study done on this where we just simply ask a lot of physicists the same questions and compare the differences in the answers they give?
I think that's an excellent idea, and I'm sure you'll be giggling most of the time because that's the problem there's most important theories such as plate tectonics, evolution. They don't question those. They don't say, oh, Darwin is right again, because that's not news. But every time Einstein is right, that's news, and so on.
Huh.
So these guys.
That's a very interesting point.
Yeah. So these guys will still come up with some disputes. It's because the theory has a lot of problems. It's sort of like, with the Big Bang. We have 25 falsifications of the Big Bang. That is, things that disprove the Big Bang. One of them is conservation. Matter and motion of matter can neither be created nor destroyed. Bingo, that's the end of Big Bang theory. But there are a whole bunch more. And so we've got those, and that's the problem with the thing. Remember they have to speed up the expanding universe and so on. So one of the silliest things, of course, is expansion of the universe. And I know a lot of people that are trying to still use expansion. If you use expansion, you'll never come up with the right answer in regard to the cosmology. It's not possible. Now, they still can do measurements. You can get light measurements, with your telescope and the spectrum and all that. But that's not what we're talking about here. Remember, one of the silliest things is in the Big Bang, of course, where you have Big Bang means you're supposed to see younger and younger things as you look further and further out. Guess what they see? What I call elderly galaxies. And elderly galaxies are like our Milky Way, 13.6 billion years old, and this is where the edge of the universe is supposed to be, at over 13 billion light years. And I think they now have these huge spiral galaxies that are about formed in 200 to 300 million years, which in our time is nothing. And so now they're trying to figure out how this could happen really fast. No, that was really silly. I can imagine all these guys sitting in a room trying to discuss how we were going to save the Big Bang, because this is the end of it with the James Webb Space Telescope doing the job.
Right. Do you think that relativity laid a framework for religious thinking in science that spread through all of science? And has this led somewhat into a dark age? Or do you think that's an exaggeration of how big this problem has spread?
No, I think you summed it up pretty well. It affects everything. Uh, what is it? Just today, I saw a New Scientist, a clickbait says, going back in time. And they got stuff like that. So the average person even thinks that these kinds of things are possible. Wormholes, going back in time, and you don't go back in time because the universe is infinite. And if you went, this is the way I explain the going back in time. If you don't mind, I talk about this. That if you look at the night sky, it's this. It can never be the same 2 nights in a row. So if you went back 100 years, you'd have to put all those stars and galaxies back to where they were 100 years ago. So that's what is going on, because time is motion, everything is in motion with respect to everything else, and that's what time is like. And so that's why it seems slower or faster depending upon exactly what you're doing and how fast you're going.
I agree that time is motion. I think Aristotle first came up with this idea. But
Sure.
some people are confused because a lot of people think of time as like a watch or a clock. So
That's how we measure it. That's all it is.
can you explain how does a clock measure time?
Yeah, well, take an hourglass. You flip it, and then the sand comes down, and so on. Well, you're measuring motion, and a clock does the same thing. That's what the Earth is. The reason we got 24-hour day is why, because that's what the rotation of the Earth is. In a year, the revolution around the sun, 365 days, it's slowing down, so you got to add a leap second and a leap year once in a while, but that's a pretty good clock, not the best. There's some now like cesium-133 that's really more accurate and so on, but never 100%, never perfectly accurate. Sorry about that, but it can be better. And so that's what we're doing. We're just trying to measure motion, and that's all that it is. And I just had, I think my last post, I think I was talking about time, what they thought time was an illusion. Do you know what an illusion is?
Yeah.
What is an illusion?
It's like a hallucination, something you think you see, but it's not actually there.
Yeah, the one I like to use is mirage that you see along a desert road when it's really hot, and you'll see these looks like water on the road. It's a flat road, right?
Yeah,
and that's an illusion because it's not really water. It's just the way the light is reflected. So anyway, that's an illusion, and so it's not an illusion. Of course, it is emotion. And now there might be an argument about whether it's real or not. So what is real? Real, we know, is real thing. You're a real thing, I'm a real thing, right? An XYZ portion of the universe. But time is not an XYZ portion. It occurs in XYZ portions of the universe, but it doesn't exist. It doesn't have XYZ dimensions. So that's quite simple. But a lot of people think time is a measurement. Like they mistake the clock for the motion. This commonly happens.
Yeah, that's a really good way to put it. I think that's where people get confused. They
Yeah.
think the clock is time, not the motion.
Yeah,
They think the
right.
measurement is the
So
time. Yeah.
let me tell people a little bit about where Einstein what door he came into with relativity, with special relativity. He confused L and T. L is length, T is time. And what he did is he substituted them. And once you did that, you're jumping. It's like apples and oranges. You can't do that. But that's what he did. And the reviewers, he didn't have very good reviewers, totally missed that. Because categorically, you can't mix categories like that. So L equals T. That's why we hear of a light year, right? What's a light year? It's the amount of time that light travels for a year. Okay, so that's a light year. And that's a distance. It's used as a distance in cosmology because that is well known. And but it's substituted there. But it doesn't make time a dimension. Sorry about that. Just can't do
No.
that. Yeah. So there's other confusions in regard to time as well, and so Einstein never understood it. If he would have tossed his stuff.
Well, it's kind of like I used the analogy. If you have like a cube of water, right, you can say it's 10 centimeters long and 1 kilogram, right? But you can't
Mhm.
say weight is a dimension of length then, right?
That's
Just,
right.
they're
Yeah.
separate, very separate concepts, right?
Yeah. Yeah. In math, I've done this. I've done multivariate analysis. Remember, I mentioned our radioactive elements that we got for volcanic ash. And we were trying to compare two volcanic ashes, and I invented the Simon coefficient, which compared the two. And so the other way you could do it is called multivariate analysis. It's a mathematical method. You get an equation for all 25 elements, and then you can compare that with other. You, that's mine. Sorry.
Oh,
I thought it was yours. No, we have a garbage truck there. Anyway, yeah, so you can get like 25 elements in this equation, and you can call them dimensions if you wish, but they're not. They're variables, and they always will be. And with string theorists, they come up with, like at least 9 and who knows, 13 or whatever dimensions. So they're not dimensions, though.
right. Okay, so I'm going to go a bit on to general relativity and the equivalence principle, and I'm very interested and curious about this. So, in the equivalence principle, they say like if you have a stationary elevator sitting on the Earth versus an elevator that's accelerating in outer space at the same speed gravity's pushing down, I guess 9.81 meters per second, right?
Yeah.
You'd have there's no experiment you could conduct in these elevators to tell them apart. And like what I was kind of wondering is like one thing that's very different in terms of physics is like when you jump on the stationary elevator on Earth, you immediately begin decelerating as soon as you leave the ground, right?
Sure.
And then when you're in outer space, as soon as you jump, you become inertial, and then the floor of the elevator catches up to you. So if everything like we kind of operate on this assumption that gravity makes everything fall at exactly the same speed. But I'm wondering, is that true on a microscopic level? Have they tried taking like a million different particles and drop them all in a vacuum, and do they fall at exactly the same rate, or is there like micro variations?
No, remember Galileo did that long ago, and you can drop a cannonball and a feather in a vacuum, get the thing to fall and hit the ground at the same time, as long as it's a vacuum, okay, and
Right.
otherwise you have resistance from air. So there's that. But remember that the pressure, what causes gravitation is the differential between the distal pressure and the proximal. Proximal is close, and the distal is so that's higher. That's always greater. So then you're going to have a difference there, and so depending on the mass has reduced the pressure. When you have the ether particles colliding with regular ordinary matter, they get decelerated, and that means their pressure is less. Remember, pressure is the activity of an
Right.
object, particularly in this case ether, or in the case of air pressure, it would be nitrogen mostly. So that's what happens, and so you have a differential like that, and remember, I'm a unienvironmental determinist, and remember, I have to bring this up sometimes because the way we decide what happens to a thing is determined by what is inside of it and what's outside of it, what's the infinite matter in motion within and without. So obviously, if you have more, let's say, neutrons, you're going to have more matter to collide with than if you don't. And so that's why you get different weights. You get different weights because there's different number of neutrons in whatever you're measuring, depending on what atom and so forth. So that's essentially, yeah, true. There is a difference there. But of course, what you're talking about with this equivalence is probably a little irrelevant to what we were talking about.
No, it's not, because like let's say you can find like let's say you find one particle, like let's say an electron or neutron. If you measure them super carefully in a vacuum, let's say one of them hits the ground slightly before the other, right? Well,
Yeah.
then you could just drop both of these particles in the elevator, and the one with a gravitational field, they'll hit the ground at a different time, and the one without the gravitational field, they'll all hit the floor of the elevator at the same time because they're just floating in space, right?
Depends on how fast they're going. See, remember, anti-gravity can be done. We do it all the time with rockets, airplanes. So a lot of people ask me, "Oh, can we do anti-gravity? Then we could travel faster than the speed of light or something like that." But we do that. That's what that elevator is doing. It's going faster. It's anti-gravity. It's going faster than 9.81 meters per second. So yeah, that's what it's doing.
Huh.
And,
So,
you might have differences in different things, but it's because remember, one of our assumptions is relativism, which says all things have characteristics that are similar to all other things, and some characteristics that are dissimilar. So you're never going to have two things. When you do an experiment, you always get a different result. If somebody who's religious and stuck to being an absolutist, they could say, but you didn't get the same result twice. You got a plus or minus. You got two different values, therefore you're wrong. They could say that, and they would be right about that. Wouldn't be exactly that wrong. 99% right, probably.
so let's say I was thinking about this here. So let's say if you had like in religious cults, one of the things I've noticed is very common tactic is the distortion of the definitions of words, right? So
Right.
one common objection I hear from the skeptic camp is the distortion of the word mass. When people say the mass increases of like a particle or whatever as you make it go faster and faster, they're
Right.
not actually talking about mass. It's not gaining protons, neutrons, and electrons. It's gaining resistance to motion, right?
Yeah.
And another one I want to talk about is acceleration, because if you use this equivalence principle of Einstein, then if you have a perfectly stationary elevator sitting on the Earth, it's accelerating, right? It's the same. He's saying Einstein is saying it's the exact same thing as this elevator in outer space that's accelerating up 9.81 meters per second, right? So in physics, would it be considered, like by modern physics, is it considered accelerating to just be sitting perfectly still, like in a chair, and not changing your velocity in any way, or am I misinterpreting the equivalence principle?
First of all, there's nothing stationary, right?
Yeah.
So people often say, well, I agree with you. You say that, all matter is in motion, but I think some matter is not in motion. And that's not true. Everything is in motion. And there's not a straight line either. If you remember Newton's first law, particle going or a body travel in a straight line and nothing happens to it, it just keeps doing that. That's inertial motion. Everything's on inertial motion. If you're in a car accident and you're traveling at some speed, you'll learn about inertia when you hit the windshield and so forth in an accident. So that's what inertia is. And I don't know, I think you were talking about the second law when you talk about F equals ma and so on. But let's go to E equals mc squared. One thing about how does this mass change as a route of E equals mc squared? Because right in relativity, one of the silliest things is that mass is converted to energy. And energy is matterless motion. It's matterless motion. It flits off and out of whatever thing is now not mass and so on. So, but really what happens is, like I explained in my paper on physical cause of E equals mc squared, is that what you have as what I call a microcosm, a thing, and then it is impacted by things, and its motions, internal motions, increase as a result. So the mass increases. What is mass? Mass is the resistance to acceleration. That's all it is. It's not simply matter. It's matter, of course, XYZ part of the universe, but it is everything in the universe always has something inside of it. So I call this thing the microcosm, and what's inside I call submicrocosms, and the ones that are outside I call supermicrocosms. So now if I want to do this, one good example I use sometimes, Martin Gardner, normally a kind of a regressive, said one important thing. When the coffee cools, mass is lost. How can that be? You can measure that, as a matter of fact. Why is that? Well, because the internal motions they're transmitted across the coffee cup boundary to the macrocosm, which is the outside, and it hits super microcosms like the air, your finger, or ether particles. And so this mass decreases. It's just mass, remember, is that a result of the motion of matter inside something, okay? And so now this cooling effect is essentially transferring some of this motion to the outside. That's all it's doing. And that's the E equals mc squared. There's nothing to do with, it's not, this is not, now the reason you have to have ether, of course, is that you don't always have air, you don't always have fingers touching the coffee cup, but you do always have ether, and ether will take some of that. So that's how we get light from the sun. It's a wave in the ether. So now this coffee cup is giving off some of this motion, is banging into this ether particles that are already moving at probably 50% greater than the speed of light locally, and then it's transferred away from the cup. And so, but did you see any mass being turned into any matterless motion? No.
I want to kind of ask this just a little, because what you're saying is kind of counterintuitive to me. So let's say I have this cup and it's full of coffee and we have it in outer space. You're saying that if the cup is hot, it'll take more force to move it. Is that correct?
Yeah.
So that's kind of interesting to me, because I imagine like heat as a whole bunch of like particles bouncing around inside, right?
Yeah, right. For one thing, you have water. So H2O molecules, one example. The steel itself, even without coffee, if it was hot, the steel is vibrating.
But right? wouldn't you have roughly like an equal amount vibrating this way and this direction?
Yeah, but that's the thing about an isolated system. It never is. It's always it's always surrounded by a macrocosm that is able to transmit that matter in motion.
So I'm kind of curious, like, so let's say you had this cup in outer space. Let's say it was 0 degrees versus 1,000 degrees. How much like more force would it take to push it approximately? Like
I don't know. It would be. One example I like to give is this one. And you got to be a football fan, sort of. Okay, American football. What you do is you have two teams, and team A is trying to not move. Team B is trying to move Team A. So Team B is crashing into A. So anyway, what you do is you now cover this first Team A with a big blanket, canvas heavy, and you put that over them. And now what do? They become very active, and they punch and they kick and they do all kinds of things. So now Team B is going to have a harder time pushing them over. Why? Because they're kicking back. They're, F equals MA this way in response to their F equals MA. So that's exactly what's happening. And so think of it that way, that whenever something is in motion internally, that increases the mass.
But what I'm wondering is that if, let's say they're kicking around randomly, right?
Yeah.
And they're kicking back against you this way, but wouldn't like an equal portion also be kicking this way?
Sure.
So wouldn't that give it some kind of forward momentum as well, or no?
No, there's all, this experiment are all in one. That's why the blanket's over top, and they're not going anywhere. So a lot of times you have to talk about the boundary of things. Like the coffee cup has its boundary, right? And so that transmittal, you can't see the motion that of the heat necessarily. You know, like you can something, but mostly not. And so that boundary is very important in this illustration.
So, let's see. Next question here is in general relativity, it makes some predictions about light being bent by gravity, and this is true. So how accurate are these predictions? Are they like, right to the microscopic calculation, or are they just somewhat accurate or not really accurate at all?
They depend on the atmosphere. Remember how they did it. Eddington's experiment in 13 was one that made Einstein the most important physicist in the world and the biggest genius. The only thing is that what he was showing in that eclipse was that, like the Einstein rings, you heard of those, same thing. What that is simply refraction. So that there's not perfectly empty space around the sun. And so during an eclipse, and in fact, you can see the corona during the eclipse as well. And so when light comes from far away and it goes past through that atmosphere, what happens to it? It has to do a little diversion. It's a refraction, right?
Right.
That's all it is. So that's what that experiment showed. And now Einstein attributed it to curved empty space and also to gravitation, like you mentioned, gravitation.
Right.
And it's not, see, light is not affected by gravitation. It is affected by an atmosphere. And this is a thing that's always ignored when the regressives talk about it. They don't talk about the atmosphere that was causing the refraction in Eddington, because that would just throw out Eddington's big experiment, and then general relativity would be disproven. But that can't happen because it's occult, that kind of stuff.
So you subscribe to this idea of, I think you mentioned in your book, I don't know if you subscribe to it, this idea of gravitons, where gravity is like caused by a mechanical motion. Is that
Well, that's what they've done, is use a new word for ether. I wasn't really appreciating this till just this last year. I read Descartes' stuff again. He said that ether is the precursor to matter, which I have in my work, and that it is the cause of gravitation and the cause of light motion. And he's right. And so that's actually what's happening. And so, they can talk about all this all they want, but gravitons are just a new name for ether.
Right. So, like, when I hear gravitons, I'm imagining all these like really small microscopic particles hitting everything, and like I guess
Sure.
they go through it and hit it from internally as well.
Sure, that's it. That's what ether does.
So I guess the question a lot of people would ask is, what causes a graviton to move? Why do the gravitons all move in the same direction? And
Yeah, remember that probably follows from Lesage. In my first edition of this book, I talked about Lesage. It was only push theory. I knew that gravitation couldn't be a pull, right? Because pull makes no sense. It's just silly. And remember that Newton had two theories. One was a pull, one was a push. And the push theory that he had was upside down because he had distal and proximal mixed up, but it still was a push theory. And it was never mentioned. People just went on to this gravitation thing because it's so fantastic. Here you have something like, what the heck happens? Are there little hooks going up to the moon and pulling it towards us, or what? And even when you open a door, in order for me to open this door, here's the door handle. Well, I have to push it. I can't go like this. Come on. I have to put my hand around it and push it. So push theory is what I knew had to happen, and so that's what I did. And so
that's an interesting point.
Yeah, and Lesage made one mistake, and that is he talked about long-range graviton or whatever travel. Okay, so that the graviton that came from a distant galaxy was the same one that hit your eyeball, okay? And that was ruled out, and I didn't realize that when I wrote that first, by aberration. Now, aberration is when you look at something and if it's far enough away, like the sun, for example, it takes 8 minutes for the sunlight to hit us. If the sun disappeared right now, you wouldn't know it for 8 minutes,
Right.
because that light is traveling towards us, and so it takes time. So if the gravitation was coming from the sun, well, then it would take 8 minutes to get here. But actually, things like that are affected by gravity are like for example, tides. They don't relate to where the moon was 8 minutes ago. That relates only to where the moon is now, and that's because not the graviton, but the ether particles are local. They're banging around just like the nitrogen in air. It's flying around, and so that's essentially what's happening, and it's just plain local, and it's a push. And again, I like it because it explains the deceleration. Remember, everybody admits that gravitation is an acceleration. Nobody says what is doing the accelerating.
Right.
And if you remember Newton's second law, an object hitting another object, it slows down, and the object it hits speeds up. And that's what you're seeing with gravity.
But like, is my understanding here correct? Like, I'm imagining gravitons as being these very small particles, and like when I drop this, a whole bunch of these small particles are colliding with it, and that's what's causing it to accelerate.
Exactly.
But my question is, so like, what causes these gravitons to have momentum? Why do the gravitons all move in this direction? And like, where do they come from, and where do they go?
Remember the top of that thing, chapstick, has a greater pressure, ether pressure, than the bottom.
Mm-hmm.
And that's why it goes towards the earth, not away. Just like take a balloon that's filled with helium.
Right.
Get the reverse in atmosphere. Where's the pressure greatest? On a balloon that's rising.
Pressure is greatest below it.
Yeah, and so then the pressure is less above it, and gravitation works the same way in reverse.
Interesting.
Yeah, right. Yeah. So remember, I submitted this paper in 2018 to 3 different really top-notch physics journals. And the best I could get is one guy said, "Oh, well, we already know the cause of gravity. It's space-time." Because Einstein's space-time is a big deal, and all it is an ether sphere around every damn thing, and that's why everything goes around in a circle, and there's no straight lines, right? So remember, Newton's first law would have everything go straight. There would never be a satellite, right? Because it would go straight, fly away, and so on. But it turns out that there's an ether sphere around every bit of ordinary matter, so that's why you have satellites staying in orbit, because the pressure away and the pressure near are different, and they're approximately equivalent, and that's why they go around in a circle, but they can't go outside that circle. It's like when you go into one of these circles they have in traffic nowadays. There's a boundary there. You got to stay on the line. So.
Right. Okay, so maybe I'll bring this back to what I was saying before. So let's say you have these 2 pens, and let's say they're exact clones of each other's, right?
Right.
Well, the amount of pressure difference won't be exactly different on top and below, because like the amount of gravitons that hit it will be approximately the same, but not identically the same, right? There'll be some small micro variations.
Ether particles, so on.
Right. So that's what I was kind of wondering about, like acceleration in a vacuum. If they're not being hit by the exact same amount of gravitons, let's say this one's being hit by 1 trillion and this one's being hit by 1 trillion and 2, right? then
Yeah,
there should be some very small micro variations in acceleration.
probably are.
Right. Has there ever been any experiments where they found any of these micro variations, or maybe it's too fine to measure? Or...
It's too fine. When you think about how many ether particles it takes to do any of this,
No.
you're talking about gajillions, and so one particle won't make a difference.
Nuts. If there was, you could use that to break the equivalence principle then, but
No, I don't think you're going to do that.
ah. Okay, so let's go a bit more into some of these experiments. The most common experiments you usually hear cited defending relativity. The first one is Michelson-Morley, and
Yeah.
I heard this one many, many times, and then the first time I looked into the actual experiment, I was like, "What? This seems." How do you go from this experiment to that conclusion, right? And
Yeah.
I think a lot of it's because it won a Nobel Prize, didn't it? I think the
I
Michelson
don't know if
Morley.
they did. I don't know. I think not. I think there were too many people that were skeptics, even in those days, and they didn't really think
Maybe
about.
I'll just Google this real quickly. Let's just see, because I'm pretty sure it did, but hold on a sec. Um, uh, yeah, it says in 1907 he received the Nobel Prize in Physics. Albert A. Michelson, according to Wikipedia. But
Oh,
anyways,
okay. All right. Yeah, I'm wrong about that then. Einstein was still throughout his life, he never got the Nobel for any relativity, and that was partly, I guess, because they didn't believe it, and they just let it slide. I mean, they're not in charge of peer review of stuff. In other words, they didn't give a report saying this is why we don't agree that Einstein should have a Nobel for it.
right. So, I guess I'll ask you, can you explain the Michelson experiment briefly, and why is it bad science? And we can probably go into the Hayfel and Keating, that one's very commonly cited, and GPS, and Rebecca, what was it, the Rebecca and Pound one? We already kind of talked a bit about that.
Yeah. Well, let me just mention, is it Michelson or Mickelson? I forget how to pronounce that. You said Michelson.
Let's say, I think it's Michelson, usually.
Yeah, Michelson and Morley. Yeah, what they were doing is sort of like trying to measure ether in their, in their basement is where they had it. It was a dorm. And the one example I give is this. It's like trying to measure the jet stream in your basement. How's that gonna work out? You don't prove that there's no air, but you don't measure it either. You don't measure
Yes.
its relation to the outside. And so this is why we're getting an elevation effect in our Michelson-Morley experiments, because as you go higher and higher, the attachment of the ether to the Earth is less. And so it declines as a result. And so that's what happens. And so their experiment was to do a fixed ether. Remember, some people did think that, like you had mentioned, there could be some things in the universe that were motionless.
Right.
And then if you hypothesize that, then ether could be the main one, and everything's supposedly built around that. And so that's kind of that idea. I'm not saying they did that exactly, but that would be essentially what would give you essentially an ether wind that you could measure. And the ether wind is being measured by these folks that have gone at higher elevations. One disproof of Einstein, some of my readers have also pointed this out, that you could do a measurement in a satellite. You could do a measurement in even a jet would give you a higher value than what we've got. The best things, I think, in Mount Wilson or something, that's about 8 kilometers per second. Remember, we're looking for a total differential of 30, and so in order to get that, you'd have to be higher and higher and higher, and so you get a satellite that's really far away too, and you'll get a result. And so that would happen, but there's no interest, of course, in regressives and cosmogonists in disproving Einstein. They only prove him right.
Well, and Michelson-Morley, the original experiment, wasn't even done in a vacuum, I think.
You don't need to vacuum. Vacuum wouldn't help, because ether is everywhere. A vacuum is not necessary because remember the elevation values I showed you?
Right.
They are not in a vacuum and they still show an increase.
So, yeah, we were saying like you can theoretically match the speed of light in water. So the way that like physicists often try to resolve that is they say, well, it's only true that you can't go you only have this invariant of light speed occurring in a space medium. Is that a accurate summary?
See, actually, that what Einstein says has nothing to do with how fast you can go. You could go faster or not, but how that could be, I don't know. Uh, the problem is that there's always something there. There's ether there, and so you're going to have like even when the Earth goes around the sun, it's interacting with ether, and so it's going to slow down, even though there's no air there. And so that's one of the things that happens. And there are other things. There are objects around, like I pointed out in one of my blogs. Remember this object that from space that's shaped like a needle? It's like an Oumuamua or something. It has a weird name. And so that is an object that if you were, and they said it was from outside the galaxy. So if you're trying to fly outside the galaxy, or even within the galaxy, you can easily hit space debris and at a high velocity, you disintegrate. So there's that problem. That's why we haven't had any alien and visitors and so on, because it's just plain impossible.
Okay, so next question. I have a couple more, then we're going to get on to some of the points in your book here, maybe more directly address it. And okay, so this I've been doing this investigation for a long time, and to me, the most convincing explanation that I've been able to find for debunking relativity is this one I talked about, where when you use the same reference point, you measure the same distance, and then there's no reason for time dilation. I think I sent you that quick video on it. Did you
that was really nice. And so, yeah, you had it right. Obviously, things going away, the waves are further apart, which you showed. Then if you're on the thing, they don't separate that way. So, because you're just sitting right there and you're talking about a frequency, which like if you use a drum or something, the same thing will happen. I've used that as an example.
Right. Okay, cool. That's pretty fast. Maybe I'll put a clip in there just to show what I'm talking about here. I'll edit that into the video.
Mm-hmm.
Next is I'm going to talk a little bit about Einstein's personal life. I don't know if you look too much into that, but this is a quote from the Jewish Post and News, taken from his letter to his first wife. And he says, "Not only children need a bit of thrashing, but also grown-ups and especially women." So, a very very strong contrast from the image we have of Einstein of this kind of jolly professor smoking a pipe, right?
Yeah, you don't see there. It's called there's different definitions for Einsteinism.
Right.
One thing that I use is that being right for the wrong reason. It's like light going around the sun or the Einstein rings and so on. Those are simply refractions. And so he was right. It's going to be bent, not because perfectly empty space was there or gravitation, but just because you have, an atmosphere. So anyway, another Einsteinism is to glorify Einstein on every possible occasion. And this would be an example of how you would do that by not mentioning any of the scandals involving his personal life and
right. So what I was kind of wondering is, like, from your point of view, do you see Einstein as like someone who's just crazy and like a very bad thinker, or do you think he's kind of like fraudulent and he's intentionally trying to make this theory so it's really hard to test and really confusing? Like, when I get into a debate, every debate just ends with space-time, and when people start bringing up space-time, everyone's just like, what? What's going on, right? It seems like it's intentionally designed in a way to just really confuse people a lot. Do you think it was more like, do you see more as like fraudulent or more as just crazy or something else?
No, I think he was just confused. He was very poor at philosophy. He didn't really know much about it. And most scientists don't. That I didn't until I studied the thing and found out the 10 assumptions of science, and that changed everything for me. But before that, we used to be empiricists. We would say, I don't need no stinking assumptions. And so the only assumptions we used were mono, they weren't bimodal. In other words, with the 10 assumptions of science, remember Collingwood is an expert on this, and he simply said that if you have a fundamental assumption, it's not provable, number one, like you can't prove the universe is infinite because you can't go to the end of the universe, and you can't prove it's finite either, and so you have to just either assume one or the other. And when you have these two assumptions, you just pick one or the other. And if you have more than one, then they have to be consupponable, a word that most people have never heard of. Consupponable means it means with supposition. So if you assume assumption one and then you have another assumption, they can't contradict each other.
Right.
So one example is causality is a result of an infinite number of microcosms producing an effect. And so, well, how can I say that? Well, with ether being trillions and jillions of particles, yeah, that's why we always get a plus or minus in every measurement we ever do. And that's because of that. And so it's because of infinity. So infinity fits so much stuff, like the second law, the explanation of that, and also this one here about causality and so forth. So that's why I like the 10 assumptions so much, because it really really solves a lot of problems.
So first thing I think is pretty interesting is this idea that outer space has temperature, because I didn't know that. I was always told outer space is absolute zero. And then I just said, well, is Glenn right? Well, I Google it up. I'm like, oh, yeah, Glenn's right. Okay. It's not absolute zero.
Yeah, right. And remember that it has a temperature because there's matter there. Every part of the universe has matter, and the matter is always in motion, and that's what temperature is.
So when you say space is not perfectly empty, you mean it has like all this kind of micro dust inside it?
Well, it has everything. Look at as far as the 2.7 goes, that could be hydrogen. There's a lot of hydrogen out in outer space. It's probably ether, but I don't know that for sure. And there's certainly ether out there. Like I said, it's the highest pressure is farthest away. So, yeah, that's what would be the case. And it varies a little bit. It's never 100% the same everywhere.
Right.
I don't know if you've seen the picture that they show.
So that brings up my next question, which I think might be pretty interesting for you. So I asked a physicist in special relativity, and they tell you all these things about distant galaxies. They'll say, like, we know this galaxy is exactly 47.221 light years away, and this planet's doing this motion at this speed and all this, for things that are extremely far away. But all these measurements are done with light, and
Right.
if space doesn't have a consistent density of junk, like let's say the Andromeda galaxy has twice as much dust floating around in it, right? Isn't that going to throw off all your measurements?
Sure.
So that's kind of an interesting, very simple answer. Okay.
Yeah.
Right.
You're never going to get exactly the same, and so depends on which. Remember, if you've got a galaxy and measure the front edge of it, that if it's like this, and you have the front edge and you have the rear edge, you get a different result.
Right.
If you can do that, and that's very difficult to do, because normally if you're just looking at it like that, and it's rotating all right, but it's rotating usually pretty slow.
Okay, so let's go into. I think the area we'll probably have the most disagreement in might be on infinity. Maybe it'll be more interesting if we pick a point that we're disagreeing, because I think just me saying I agree with you, most of it I agree with you on, but we'll start more with the things we disagree with. So, and maybe we'll end up convincing each other or something. So on infinity, you say that everything is infinitely microdivisible, and that everything can go on forever. Like if I just keep traveling north, there is no end to north. I can just keep moving in this direction.
There you go.
Infinitely. So in my view, like I've heard arguments for and against it, and I'm more in the camp of against at least infinite division. I think that like if you have infinite division, you run into this problem of Zeno's paradox, where like if you travel half and then a quarter, then an eighth and a 16th, there's always some distance, and you can never reach the end of something, right?
So you remember what a paradox is? It's a contradiction. It always has an incorrect assumption.
Yes.
Okay, so he's doing this slicing in a dice, and it's an impairment. It's not an experiment. It's just in his mind. And this is a lot of what Einstein was doing. I even invented a word for it. You might see it in my books. It's not an experiment, but an impairment. So it's something that you have drummed up in your mind, and you say the world should be like this. But in my experience, that's not how the world is. It's always different.
Right.
And so in this case, he's just infinity and scale are not really relative. So every time you split something, then you can split it again. There's no end to that. That's infinitum. There's nobody in math is going to say, oh yeah, I now have found the last part, the last thing, and that's called finite universe theory, and that's what Newton used. And so a lot of people have used that.
But in math is like we talk about, math is an idealization, right?
Yeah, that's right.
But let's say like I mean, just from a practical standpoint, I think like let's say if what size, like let's say we're just building a tower, right, and we're stacking blocks to reach like a finite limit, like let's say a length of 2, right? What size of block could you stack an infinite amount of and reach a finite size? I think it would have to diverge to infinity if it's any quantity larger than 0, right?
Well, let me explain how we handle a little bit of your conundrum. That's
how do you resolve that? That I'm interested to know.
We have another book. I could show it to you next time. I can dig it up, but it's has called Universal Cycle Theory. And essentially what we talk about there, we talk about ether there as well. And ether, like everything, has to have submicrocosms within each particle.
Right.
So we call that ether 2. And those have to have particles within them. We call that ether 3. And there's no end to that. So that's what matter is. That's what your so-called empty space is. The reason things can move is that there are weaker things that can be trodden over. Like if you're, say, a linebacker and you hit somebody that's smaller, you can knock them over, right? So that's what happens throughout the universe. It's the big guys hitting the little guys. And that's essentially what you're having. So when you say, if you finitize it by saying, I have 10 centimeters and I have 1 centimeter blocks, and then how many of those can I have? That's finite. That's always finite. But infinity doesn't work that way. There's always something smaller. There's always somebody smaller than you, right? And bigger.
Right.
I've noticed that too.
So I'm still not like, and then I guess like for you talk about this in your book. Some people object to infinity because you'd have an infinite amount of light, and maybe you want to explain this paradox. Maybe you can explain it better. So some people are saying like it would never get dark at nighttime because there's an infinite amount of light.
Oh, yeah, right. That's
a
famous paradox, and that's of course based on the theory that light is traveling through a perfectly empty space as a particle, and so that's not true. And so the question is, and of course it goes back to cosmological redshift, which is explained as a reason for the expanding universe. And actually what it is follows Zwicky's tired light theory, and which essentially says that a medium, of course, determines the velocity of light. So that's why light doesn't slow down with distance. Every other particle does. You throw a baseball, slows down. Shoot a bullet, slows down. Yeah, particles do that. That's called a classical particle. So what Einstein was inventing was a non-classical particle, one that didn't slow down, which was a magical kind of particle, and one reason it had to have no mass, whatever, and all kinds of other silly attributes. But essentially, The cosmological redshift essentially is a reduction in energy with distance, which happens to everything in the universe. And so it then gives us a good measure of distance because it shows the shift in the wavelength. That's what we use. So when they measure these precise 43 million light years or whatever, that is all based on the redshift.
Right.
And that's very precise. You can measure these wavelengths really precisely, and you'll see values going out to, well, I don't know, 13.014 or something like that.
All right. So next thing I want to go into here, let's try to cover everything where we have another 22 minutes here. So
Okay.
let's see, what have we got on the list? You mentioned in your book that Einstein stole the E equals mc squared equation from Maxwell.
Right.
There's pretty strong evidence for that, or is it?
Oh,
I
yeah,
saw the
I
citation, but I didn't read the paper.
No, I give a quote on it, and he didn't present it as a paper separately. I think it's in one of his books later on. And it was done in 1862, and I'm relying on one of the reformists who I give a reference to his work, and he had written a nice paper on it. It's been removed from the internet since, so I think that somebody got at it. But yeah, he had done that. What he was interested in was the opposite of fission. In other words, he was interested in why do plants increase mass? That's so when sunlight hits something, why does the mass increase? Well, there were other reasons for it, but essentially what he was saying, it'll increase the velocity of the particles within, and that's an absorption of motion, absorption of light or whatever, and that's what plants do that have chlorophyll and so on. That's what they're doing. So he wasn't interested in the part like with fission. You have things coming apart, so then you have the energy or the motion being transmitted outside of the thing, so the mass decreases.
Right. Okay, so sorry, I'll try to keep moving here. I'm kind of juggling all these questions. So one common thing I've noticed from the apologists is they always say that you're making a straw man of relativity when people claim that it's about time travel and alternate realities. Relativity has nothing to do with that. And in fact, that's a quote from Peter Donis, the guy who runs the physicsforum.com.
Oh yeah, yeah.
So I think that's nonsense. I don't think you can have time dilation without time travel. Aren't you traveling through time every time you have any time dilation effect? Like,
well,
if I jump onto an airplane, then my time's slowing down. So how is that not time travel? You know, I'm coming back to Earth 1 second younger. Isn't that time travel?
yeah, that's kind of what they were doing. You know, it's just a Doppler effect for that twin paradox thing where your twin flies away and comes back. They're really both the same age. They don't change.
Right.
In fact, they don't. Not just in impairment, but also as a fact, does not happen.
I think a lot of people also don't understand this. Like, I think a lot of people are confused on time. Like, for example, let's say we have an electric clock, right? Well, electricity flows faster in a cold wire than a hot wire. Is that correct?
A cold wire?
I think,
it would be a hot wire probably, but
anyway, so
I'm not sure.
We might have to look that up. Yeah.
Yeah.
Anyways, so like if I had an electric clock, like if the temperature of the wire gets hotter or colder, that could affect how we keep track of time, right? But it doesn't mean time itself is slowing down. That's just the measuring device, right?
Yeah, all we're talking about is measurement.
Right. So this is what, like, I think one of the greatest errors, and you've mentioned this many times, which is that like people are using a clock to say that this is motion, whereas it's just like a tool for measuring motion, right?
Right.
And like another example is if I take a gravity-powered clock and I put it on the moon, it's not going to be an accurate way to keep track of time, right? We'd probably want to use an electric clock in that case, right? So math does not prove the real world. The real world proves math. So a
Right.
lot of people will disagree with you there. Can
Oh,
you elaborate on that?
no, that's just the way it is. I've done tons of math, and that's how it always was for me. And I invent the similarity coefficient. It says that something that's perfectly similar to something else gives you a value of 1.0, right?
Right.
And if it's perfectly different, then it gives you a value of 0. But that never happens. The real world never has two things identical. No two chemical analyses are going to be exactly the same. They're going to be a variation and so on. So that's what always happens with, and that's why we have the plus or minus. And that you still could have a hypothesis that is based on a false assumption and use that then to build math. And that's what Einstein did. So anyway, you can do all kinds of imaginings, and that's what religion's all about. That's why there's 4,000 religions, because people have imagined various things that, and they don't agree with each other, and so that's what happens. And so imagination is wonderful. Remember, Einstein said, imagination is wonderful because it goes around the earth. And most people have imaginations, right? If you have a dream, you're going to think about that. And so, like I pointed out in the book, it's like religion is based on dreams and imaginings, right? And a lot of our math is based on dreams and imaginings. Remember Kekule's experiment, not experiment, but his thought experiment was where he had these carbon chains that were wiggling around, and he's sitting by the fireplace, he falls asleep, and one of those chains hooks up with his tail, and oh man, he gets the best ring that ever was. It's benzene ring, which is most of organic chemistry, and that was how he did it. It was a dream.
Huh.
So, yeah, it's like one of my favorite profs said, "Oh, I gather information during the day, and at night I dream about it and solve the problem."
Huh.
I've done the same thing, so that's how you do it. But you have to then test it in the real world, and that's the difference between science and religion, because you don't end up testing it in the real world.
Right. Um, so next, I'll throw out you here is the modern. I think in modern day thinking, paradoxes are very commonly accepted. All these contradictions. I think like accepting contradictions and paradoxes is a very normal part of modern thought.
Yeah, that's
And
because it's based on religion. So you have tremendous amount of contradictions in religion. And so, if you're talking about one religion talks about walking on water, virgin birth, living after dying, and so forth, those all involve contradictions with actual things. So, yeah, and the average person expects contradictions in whatever they read, and the media obliges. Like I was just saying, I wrote this blog about time is an illusion. Gee whiz. and so forth. So New Science, by the way, New Scientist is this magazine I've been reading for 40 years, and it has Big Bang and relativity stuff every month almost. It's like, remember, Reader's Digest used to have an article on sex every month, and now they have one on Big Bang every month.
ugh.
so,
Okay, well,
so
I'll have to read your book on the Big Bang, and maybe we'll have a future interview on that. Getting near the end of my list here. So, nobody could know about nonsensible things. This kind of goes more into quantum mechanics, and I was talking about this a bit. So, I think like a lot of quantum mechanics goes by the principle of observing that which is unobservable. And I'm kind of curious, what are your thoughts on like quantum mechanics and observer-dependent reality? That's a very big concept. Like, nothing happens in reality. Everything's in a superposition until you watch it, right?
yeah, remember that's what immaterialists do. This is the first assumption of religion, that there's more to the universe than matter. And that's what they're saying. So that's essentially what Deepak Chopra is. He's really into, and Berkeley was too,
But
and
this
that's
is
what that is. And
Are you familiar with the Copenhagen interpretation in quantum
yeah,
mechanics?
right. So
That's
same thing.
basically what it is,
So,
right?
well, they're kind of saying unless I observe it, it doesn't exist. Okay, and remember that is also an outgrowth of empiricism. Empiricism said the same thing. If I can't feel it, taste it, touch it, or whatever, it doesn't exist. And that was always wrong because eventually you did find something. Like, for example, there's nitrogen in air. It wasn't just nothing, and so forth. So that's essentially what has been used, and it's still used. That's that's what Einstein was using empiricism. That's why he objected to quantum mechanics because they didn't have any real good proof. They were. It was more bullshit than he had even. You know, they were talking about. You know, they're talking about. If I don't see that particle, it doesn't exist, right? So yeah. Or if I don't measure it, you don't. That's not the measure. You can have a proof for something that you imagine. Okay, fine. Now you've got some evidence. Well, if you don't have any evidence, then what do you do? Now, one of the things I'll give you a little bit on quantum mechanics is that you're talking about the velocity and the position of a particle, right?
Right.
And that's correct. If you can't measure the position and the velocity at the same time without interfering with it.
Right.
So you measure it, say, with a baseball bat, and by the time you hit it, it's gone, and now its velocity is totally different than whatever it was. So that's what essentially quantum mechanics is.
Right.
Just think about it. And they try to tell us that, well, these are such small particles that they have special properties all their own. Well, some of them, but they got some basic properties. Number one, any particle has to have mass inside of it. Okay, that's just one of our assumptions. We don't always prove that, but that's one of the assumptions we use, and that's been pretty good. Just like conservation, conservation of matter and motion. That's dang good assumption. And so the rest of the 10 assumptions are the same way, same darn way. That's why you got to have those. And you got to use it. See, infinity, you got all kinds of objections to infinity, of course. You have to choose. Do you want to make headway or not? Infinity is how you do it, not by finity. Not by having the universe explode out of nothing. Come on.
So, I guess one last thing we'll go into maybe, or maybe I'll let you. I'll give one more thing, and then I'll let you kind of go into any other points you want to cover, because I've been asking all these questions, but there's probably some things you want to talk about and elaborate on. Okay, last one I was going to talk about is action at a distance. We talk about this in your book. So, to me, like intuitively, it makes a lot more sense that something moves because something hits it. There's a physical explanation, right?
Yeah.
There isn't just these fields, but probably 99% of people, like when we think of gravity, when we think of a magnet, we just kind of imagine it as this almost like there's this spirit or force just pulling it. So to me, that's interesting. I never thought about that until I read your book. So, but is it possible? The universe can have some weird things too, right? Like, how do you know that there isn't just some weird force that can act at a distance?
I don't know. A lot of forces do.
But there's this invisible force of magnetism where nothing's physically moving it, right?
Yeah.
How do we know the universe doesn't
that's only, remember Einstein mentioned that too, and one of his big errors was that he assumed that there was no ether, and that what you have in regard to gravitation and magnetism is matterless motion, a field, mind you, a field.
Right.
Well, but the field has to have particles in it according to me and other people. And so that's what he missed. He didn't have any particles in it. So he didn't have matter and motion. So the big thing about one of the big differences between Einstein and classical mechanics is classical mechanics said you had to have one object hitting another, like you were pointing out. That's classical mechanics. And when you don't have that object, then you have a kinetic theory. You've got this thing is moving, but you don't know what moved it. And that's what you're talking about there.
Yeah.
And so that's really important. That's really important that Einstein said, no, there wasn't anything there, that it was immaterial. And then that fit with his original thesis that ether did not exist.
Well, there's a whole lot more questions I want to ask you, but we're running out of time here. Maybe we'll have a second interview in the future. We can put it in the Big Bang one if we do that.
Yeah, sure.
And I'll say, is there anything you wanted to get into, or any topics you want to cover, or questions you have for me?
Yeah, I think you have to read our books and catch up to where things are going now. See, you have to decide whether this is what is going to answer the questions for you or not. I mean, if you're religious, you shouldn't read our books, because that'll just confuse you and make you have doubts about your own religion and so on. And you can do it. A lot of people do. They'll read. I get people that read. They don't necessarily read my stuff, because I can ask questions and they don't know the answers to. So that's how it works. But yeah, so this whole idea of things crashing into each other, that's a simple enough thing. If you're going to have gravitation, you've got an acceleration, so then you've got to have an accelerant. Now, the space-time thing is all that talks about is essentially what we have is an ether sphere around every object, and that's the space-time that Einstein, that's why he was right. So that whenever you have a deflection like the Einstein rings, that's space-time, right? Space-time is not, first of all, is not empty, not perfectly empty space, and it's not just time. Time is what we use to measure some of the deflections, perhaps, but that's all that is. So there's a lot of things in relativity we certainly haven't covered, and we could cover a couple more times on that if you want.
Nobody ever hears these views coming from physicists, so I wonder, is there this active suppression, or is it just do you think there's this active suppression of dissent, or just?
Yeah, you definitely got that. Like I said, we have disproven Einstein, 1,000 times, probably a couple thousand times at least. And have you seen any talks on anybody who was opposed to Einstein?
No.
Who made any sense? Who made any sense at all? So, yeah. So that's kind of definitely a censorship, and we do that. I've been an editor too, and I would reject papers that were nonsense, and that's just how you do it. Now you have to know what's nonsense and what's sense. So that's the problem.
Right.
And so peer review, if that doesn't fit the paradigm, which is what we call the Big Bang and relativity, then you throw it out. And so that's why, like the guy said, they already know what gravity is caused by. So don't. And causes are not collisions. That's not what space-time's about.
Right.
So, or gravity, according to Einstein, right? So yeah. So there you go. And so that's what they're using as their guide, and that'll all change eventually once things are getting tough right now for the cosmogonists because of the James Webb, photos kind of disproving their stuff. Basically, in the mainstream, you don't get published, and that's for obvious reasons, because you contradict their story, and paradigms don't like that, and especially when they're not very good paradigms. So, sort of like, plate tectonics is a proven theory. Nobody says, "Oh, proven right again."
Right.
In earth science, that's all we use. I mean, that's how it works. So for a while, there was a problem, and people were trying to figure out why mountains were rising, and they couldn't figure that out. And so when plate tectonics came along, and you had subduction with one, plate going on the other and pushing up like the Rocky Mountains are. Actually, I should say Cascades better ones because more recent. But anyway, that's the thing that we use all the time. So, like I said, I've published over 500 things, and I think I had one that was rejected because the guy was competing to produce the same work but with the nuclear reactor. And Science magazine was good because the editor realized what was happening, and he essentially accepted that publication. And then one other time I directly contradicted some consultants that, consultants, we get paid lots of money to do that, and obviously they didn't like their ideas chastised, and so they got our paper rejected. So other than that, mostly not. As an editor, I normally just help the authors out, give them some help. And of course, I was the one to select, in many cases, as the editor, you select the reviewers. So if somebody states something and you think it might be wrong, then you send it to that person who might object, because you want to find out both sides. And so I used to do that. And mostly the stuff in science is what, I don't know if you read Structure of Scientific Revolutions by Kuhn.
No.
Yeah, it's a book you ought to read. It has a good starting point for you to understand what paradigms are. And it's not just one theory, but it's a whole bunch of stuff. And it includes everybody who ever wrote about it. So now billions of dollars have been spent on relativity and cosmology. So that's one reason that you don't have people accepting anything else. They spent their whole life on a theory that's not correct is quite embarrassing. And so the ones that realize that don't say anything. And so the other ones that don't know very much about it will try to defend it, as much as they can. And so on the internet, you get a few people like Siegel. I don't know if you've seen his stuff. He's on Medium, and he has a thing called "It Happened with a Bang" or something like that. Started with a bang.
Steven Siegel?
He writes about Big Bang stuff.
Is it Steven Siegel?
Siegel.
Ah, he's the computer guy, isn't he?
I don't know if he is or isn't.
I think I saw one of his videos on AI. He was saying like AI is a bunch of BS. Like they're just really grossly exaggerating the intelligence and all that.
He may have that as his work and so on, and it's not a bunch of BS because it was. I remember one time I checked it when ChatGPT just first came out. I asked them who Glenn Borgert was, and they said, well, he's in Texas and he's done some nuclear physics stuff, but he died in 2019. And well, that was quite an exaggeration.
Huh.
It's a different Glenn Borgert. So they would get, and it's funny because I have a site that's called glennborgert.com, which hooks up to all my stuff, and obviously Chat didn't even check that out. So that would be the first thing you would do if you're a decent AI. And but recently, it's been very good. I've got a friend, Jesse Whitwer, who's in Edmonton, and really great guy, and he checked out Perplexity. That's another AI. I don't know if you heard of it, but it combines chat and others. And he asked them, what about this possibility of there being an ether? And then, of course, Perplexity says, no, that's not possible. And then, but what if it was? What would happen? And he went through the whole thing. After a couple of weeks, he got all this material from Perplexity, and finally Perplexity is starting to come around and saying, yeah, that could possibly be true. And at the end, Jesse asked him, well, which one is correct, the Big Bang or infinite universe theory? And well, Perplexity said infinite universe theory, about 99% chance. And then Jesse says, well, how come only 99%? And he said, well, most people think the other theory is correct. And so then he said, well, just because a whole bunch of people believe something, does that make it correct? Which is one of the arguments, fallacious arguments you can make. So anyway, finally, Perplexity said, oh, you're right, it's 100%. So I'm trying to get Jesse to write that as a little book. There's quite a bit of stuff from AI, so it's definitely not BS, and it's just only going to get better and better. And eventually it's going to take over a lot of jobs. Like, say you're a lawyer and you're looking up case law. You put in Perplexity, it tells you all the cases. And in science, I've been checking a lot of that stuff out on questions I have in science, and comes up with all kinds of good answers. Plus, it gives the references. You can check them out if you like. You know, some of it's bullshit because you're picking it off of, you know, all kinds of
Yeah,
media.
but like even
You check it out if you want.
I use it. I use it a heck of a lot, right? Like, and when I do check up the references, they're often wrong. Like, it makes a ton of mistakes in referencing.
That's
But
because you're
like,
doing relativity. I don't do that much on relativity.
yeah. Well, that's another funny thing because I asked the AI, is it programmed neutrally? Because it told me all this information that was weird. So I asked it like, are you just making up information now? And it said yes. So I said like, what's going on? And it said that it's programmed to fabricate and make up information in order to defend relativity.
Is that right?
Yeah, I can show you. I have it on. I have like a screenshot of it. I can
Oh,
even send you it.
really?
Yeah.
I'd love to have the copy of that because I need that kind of stuff. And
Sure.
yeah,
I'll
I
send you
think
that.
that's always true. You know, that's it's got to defend the current work, and so that's what it's doing. So if you ask Perplexity today or Chat, they won't say that IoT is better because they see this is a what the beauty about Perplexity is it keeps a chain of your discussion and it
Yeah.
saves it too. Are you maybe is Chat? We're using Chat. Which one were you
Oh, that
using?
was Meta.
Oh, okay. Uh, well, anyway, Perplexity is very good at keeping a chat keeps. In other words, it'll ask what other questions you want to ask about this topic, you know, and you just go through it. So
Right.